What you are witnessing is not just a landing. It is one of the most fragile, high-stakes moments in human history. The descent of the Eagle lunar module during the Apollo 11 moon landing wasn't smooth, and it certainly wasn't guaranteed. Inside that small, angular spacecraft, Neil Armstrong and Buzz Aldrin were doing something no human had ever done before, flying manually over an alien world with no room for error. The computer on board was already overloaded, throwing warning alarms that could have forced an abort. The landing site wasn't safe, filled with rocks and craters that could tip the spacecraft over. And as the seconds ticked down, fuel levels dropped dangerously low. Armstrong made a decision. He took control, guiding the Eagle forward, searching for a safer spot, stretching every last drop of fuel. Mission Control watched in silence. There were no guarantees they would make it. When the spacecraft finally touched down, they had less than half a minute of fuel left. 30 seconds separated success from disaster. That was the reality of Apollo, a mission built on precision, simplicity, and just enough technology to get the job done. Now fast forward to today, and everything has changed. The Starship HLS, developed by SpaceX under NASA's Artemis Program, represents not just an upgrade, but a complete redefinition of what a lunar mission is supposed to be. Because this time, the goal isn't just to visit the moon, it's to stay. That single shift, from exploration to permanence, forces engineers to rethink everything from the ground up. Apollo was about efficiency. Artemis is about infrastructure. Apollo minimized risk through simplicity. Artemis accepts complexity in exchange for capability, and nowhere is that difference more visible than in Starship. At over 50 meters tall, it doesn't just land on the moon, it towers over it. It's closer to a building than a spacecraft. Inside, there is enough volume to carry not just astronauts, but entire mission architectures, habitats, rovers, scientific equipment, power systems, everything needed to begin constructing a sustained human presence. This is no longer a mission. It's the beginning of an ecosystem. But building that ecosystem introduces challenges on a scale we've never faced before. Let's start with the biggest one. Getting there. Unlike the Saturn V rocket of Apollo, which launched everything in one massive all-or-nothing attempt, Starship depends on something far more complex: orbital assembly and refueling. The Starship HLS cannot leave Earth fully fueled. It's simply too large. So instead, it must be launched partially empty, placed into orbit, and then refueled by multiple tanker spacecraft. Picture this. One Starship launches and waits in orbit. Then another launches, docks with it, and transfers cryogenic propellant. Then another, and another. Each one adding more fuel, building toward a full tank. This isn't just one mission. It's a chain reaction of missions. And every single step has to work perfectly. Docking in orbit is already complex. Now imagine doing it repeatedly, with massive spacecraft, while transferring supercooled liquid methane and oxygen in microgravity. Fluids that don't behave the way they do on Earth. They float. They shift unpredictably. They boil off if not properly managed. This kind of large-scale orbital refueling has never been demonstrated in a real mission. Not once. And without it, Starship doesn't even reach the moon. But let's assume it works. Let's assume everything goes perfectly, and Starship begins its journey across the 384,000 kilometers separating Earth from the moon. The next challenge is landing. During Apollo, the lunar module was small, light, and stable. Its low center of gravity made it forgiving. It could tolerate slight slopes, uneven ground, minor errors. Starship doesn't have that luxury. At its height, even a small tilt becomes dangerous. A few degrees off balance could mean tipping over, a catastrophic failure on a world where rescue is nearly impossible. To compensate, engineers have designed wider landing legs, advanced sensors, and autonomous hazard detection systems capable of scanning the surface in real time. But even with all that, the physics doesn't change. Bigger means harder to control. And then, there's something even more unpredictable: the surface itself. The moon is covered in regolith, a fine, powdery dust formed over billions of years. During Apollo, this dust was already a nightmare. It clung to everything, scratched surfaces, damaged seals, and reduced visibility. Now imagine the effect of engines far more powerful than anything used before. As Starship descends, its engines will blast the surface with enormous force, kicking up vast clouds of dust. This dust can obscure the landing site, interfere with sensors, and potentially damage critical systems. Worse, we don't fully understand how it behaves at this scale. This isn't just a nuisance, it's a risk multiplier. And even if the landing succeeds, the challenges are far from over. Because now you have a spacecraft the height of a skyscraper, sitting on the moon. The astronauts are inside, 30 to 35 meters above the surface. There's no simple way down. No ladder long enough. No quick exit. The solution? An elevator. A mechanical system designed to lower astronauts and equipment safely to the surface. It sounds simple, but it isn't. It must operate flawlessly in extreme conditions. Vacuum, temperature extremes, dust contamination. Because if it fails, the consequences are severe. If it gets stuck while astronauts are on the surface, they may not be able to return to the spacecraft. If it fails while they are inside, they may not be able to exit at all. There are no easy fixes on the moon. Now contrast all of this with the Blue Moon Mark II, developed by Blue Origin. Where Starship pushes boundaries, Blue Moon pulls back. It is smaller, simpler, and more focused. At around 16 meters tall, it has a much lower center of gravity, making it naturally more stable during landing. It doesn't rely on massive orbital refueling campaigns. Its design is closer in spirit to Apollo, refined, modernized, but grounded in proven principles. Its BE-7 engine, using liquid hydrogen and oxygen, provides efficient propulsion tailored for lunar missions. It's not trying to do everything. It's trying to do one thing well: deliver astronauts safely. And that difference in philosophy matters. Because in space, complexity is the enemy of reliability. But capability requires complexity. And that's the trade-off Artemis is navigating. These two systems are not rivals. They are partners. Starship is the builder. Blue Moon is the transporter. One delivers the infrastructure. The other sustains human presence. Together, they form the backbone of a long-term lunar strategy. But even with both systems in development, one factor continues to dominate everything else: time. The Artemis Thumquo has already proven that we can send humans around the moon again. The program is moving forward, but orbiting the moon and landing on it are fundamentally different challenges. The mission originally intended to achieve that landing, Artemis III, has faced delays and changes. Now, the first true landing is expected with Artemis IV, currently targeted for 2028. But space timelines have a habit of slipping. Every delay in one system affects all the others. Spacesuits must be ready. Life support systems must be validated. Launch schedules must align. Communication networks must function flawlessly across vast distances. And, most importantly, all of these systems must work together. Not individually, not in tests. Together, for the first time, hundreds of thousands of kilometers from Earth. And that's where the real uncertainty lies. Because as of today, several of these technologies remain unproven at the scale required. Orbital refueling hasn't been demonstrated in full. Large-scale lunar landings like Starships haven't been attempted. Long-duration surface operations are still being developed. So when people ask whether we will return to the moon before 2030, the honest answer isn't simple. It's possible. But it's incredibly ambitious. Because this isn't Apollo. Apollo was about reaching the moon once. Artemis is about building something that lasts. And that means solving problems we've never solved before, at a scale we've never attempted, within a timeline that leaves very little room for failure. But if it works, if everything comes together, this won't just be another historic moment. It will be the start of a new chapter in human history. A chapter where the moon is no longer a distant destination, but a place we return to again and again. A place where we build, explore, and prepare for what comes next. Mars. Deep space. The future beyond Earth. And this time, we won't just leave footprints in the dust. We'll leave a presence.